So this is a tough question, and it's one which really has a lot to do in there. There's a lot involved in different areas of physics. So take this one slowly if you can. Um, the first thing to recognize is that this is a question about masses and temperature. So you're going to want to use your equation for specific heat capacity, which is delta Q equal to mc delta T. You might not always see the delta Q in there. We really do think of heat as being a transfer of energy. And I think it's useful in this case to use this delta. We'll see why that is in a second. Now, whenever we have multiple liquids or substances mixing together, then we're aware that energy is going to flow from one to the other. And in this case, it's not clear to see who is going to gain energy and who's going to lose energy. And one of the ways that we can make this a bit easier on ourselves is to recognize that energy must be conserved, which must mean that regardless of who gains or loses energy, the total change in the energy must be zero. So I'm going to express this in this way, that substances 1, 2, and 3 are all going to have a change in energy, and that's the delta Q. However, I know that the changes are going to add up to zero. So this is the conservation of energy. It means we don't gain or lose any energy during this time. Everything balances out. Now, what I can do is combine these two equations. I can put in my M1, C1, delta T1, etc. for each of the substances. And notice here, I'm not saying anyone's winning or losing. I'm just saying that there is a change in the energy of some sort. Now we can start being clever. We can recognize that these are the same liquid. And so that means that this C is going to cancel. C1, 2, and 3 are all going to be the same because they're the same liquid and therefore they have the same value of C. We can also put in the values for the mass. And we notice there that mass 1 is 2m. The second mass is also 2m. The third mass is simply m. So my equation has got a bit simpler. And again, we're going to be able to cancel those m's because the m's are the same as well. The final step is to recognize that eventually all of our substances are going to reach the same equilibrium temperature, and we're going to call that big T. The change in the temperature is going to be big T, take away the initial temperature. So for the case of sample 1, we're going to have T take away 60, sample 2, T take away 30, and sample 3, well, it started at 0 degrees, and so therefore that's going to be T take away 0. This is where we can do a bit of maths. You can see we've got 5t here, and then we've got some other numbers that we can add up, 260, 230s, add them together. We end up with an expression which is simply that 5t is equal to 180. And if we simply divide by 5, we end up with T equal to 36 degrees Celsius. And that's our answer B. And as I say, there is quite a lot going on here. This is one of those ones where you take some time thinking about it because it's a really good test of your understanding of conservation of energy and how this applies to systems where temperatures are changing.